Let us apply this implicit function theorem, or IFT for short, for our example with the unit circle. Equation. The same point as earlier. Okay, let's check whether it's applicable. The theorem is applicable to this particular equation considered at this point. First of all, the function, capital F, is x squared plus y squared minus 1, and it is continuously differentiable for all x, y values. Secondly, when we substitute the coordinates into the equation, they satisfy this equation. Easy to check. Now, what's df over dy? This is 2y, and when we substitute this number, it's not 0, for y equals 1 over the square root of 2. So the theorem is applicable, and it claims, as we have learned, that implicit function exists, and this function on some interval is continuously differentiable. When we substitute 1 over the square root of 2, it takes the same value, and when we substitute this function into equation, so this equation is satisfied identically within the same interval. So as for the interval, this theorem doesn't give a clue, simply because this theorem is of local nature. We can guarantee that such an interval exists. What about the derivative at this point? So according to the formula, we need to substitute into the denominator 2y taken at this value, which becomes the square root of 2. What about df over dx? df over dx at this point is also square root of 2. So we have negative 1. And clearly, if we draw the tangent line to the unit circle at this point, this angle, this is an acute angle whose value is definitely 45 degrees, and this is an obtuse, so we can easily check that this is a correct result. A word of caution should be said here. What if we try to apply IFT to the point x0, 1, y0, 0? Well, first of all, the condition of the IFT is not met, because df over dy at this point is 0, because y0 is 0. But we need to understand what's the problem here. The problem here is as follows. If we're trying to solve the equation in terms of y as a function of x, it's impossible to do so within the neighborhood of the given point x0, 1, y0, 0. Because what part of the unit circle should we choose as the graph of the implicit function? Should it lie in the upper half plane or lower half plane? Impossible to tell. And also, if we consider points which lie to the right of this point, there is no graph there at all. And when we're looking for the function should be defined in some neighborhood around the point. A question whether it's possible to find implicit function even if df over dy is 0 at a given point. If df over dy is 0 at a given point, probably another derivative, df over dx, at this point is not 0. This is exactly what happens here at a given point, where derivative equals to x and x is 1, so it's not 0. We can reformulate the theorem, and we claim the result that there is a function also implicitly defined, a function x as a function of y. So here y is an independent variable and x is dependent variable. And it exists in some neighborhood of the given point, although the interval where this function is defined is along y-axis. And moreover, we can try to find derivative. This is x prime with respect to y. And, well, if we consider this particular problem, we need to use the formula. Here we have number 2 in the denominator, and here we have 0. So we have 0 here. This is a result for this particular unit circle, but we can try to do the same in case then the gradient of the function which defines this equation doesn't turn 0 at a given point. Now let's consider an example, or rather problem, from microeconomic theory. Let us suppose there is a monopolist whose profit can be found by the formula. This is the inverse demand function, P of y, where y is the output of the monopolist. So that's this product provides the revenue, and the marginal costs of the monopoly is constant, and this value is c. So we multiply, in order to find, there are no fixed costs, in order to find the total cost function, we multiply the marginal costs by y, and this is a problem of maximization of profit with respect to the output. What's given, what information is provided about demand? The demand function P of y belongs to C2 class of functions. That means that it has the second order derivative, which is also continuous. And what is the problem we are going to set and solve? So the monopoly maximizes its profit. So in order to find the output of the monopoly, we need to find the first derivative of the profit, and that first order condition looks like n equals 0. Also, let us assume that the second order condition is also valid, meaning that when we find the solution of this equation, I'll be using notation y and with the upper script m indicating the output of the monopolist. So let's suppose the second order derivative of the profit at this value ym is negative. That provides the maximization of the profit at a given point. Now the question is how to find derivative of this output with respect to the value of the marginal costs, which is given by C. So that this is a question number 1. And the question number 2, how to find the derivative of the monopoly price, which will be denoted by PM with respect to the same level of marginal cost DC. So that's question number 2. And in order to find answers to these questions, once again we'll apply IFT.